Hello, BC Calc students. This is going to be day 38 in your packet, and today we're talking about the concept of slope fields. So slope fields are really awesome because what we're going to do is take a look at how we've talked about differential equations in an algebraic perspective so far, and that's our concept of taking antiderivatives. And the nice thing about finding antiderivatives is we have a lot of rules that we should be pretty familiar with. So we know how to find antiderivatives of polynomial functions pretty easily. We can do that with radical functions. We can do it with some trig functions. And they're going to start getting a little bit more complicated, and we'll find other techniques that will allow us to find antiderivatives. But for things that we're not sure about quite yet, we're going to talk about a graphical perspective today. And the graphical perspective to solve a differential equation is this concept of slope fields. So if we look at this example right here, given dy dx equals 1 over 1 plus x squared, what could y be? So we're thinking about, what's the original function whose derivative is 1 over 1 plus x squared? And that's not very easy for us to do at this stage in the game. We're not really sure what that is, right? There's no good rule for us to apply. Even if I kind of made this into a negative exponent type thing, it's definitely too complicated for us at this stage to determine what the antiderivative is algebraically. So we're going to eventually come back to that example, but what we need to do is we're going to approach it from slope fields, the graphical perspective, to be able to determine that. And I think let's start with one that we know. If we know dy dx equals 2x, according to the anti-power rule, we know that y would equal x squared plus some constant c. Anything of this form, the derivative would be 2x. So in order to figure out what that solution looks like graphically, we have this kind of dot grid over here. And what we're going to do is at each of these corresponding dot locations, the coordinate 1, 0 or the coordinate 2, 1, we're going to sketch what the slope would be at those corresponding locations. And the slope is according to that dy dx is equal to 2x. So for example, if we start by considering what happens when x equals 1, and let's go at this point right here, x equals 1 and y equals 0. Well, you'll notice that our dy dx equation only is dependent on x. So 2 times 1 would be 2 for the slope there. And if I kind of move up the line there, like what if I went to 1, 1, let's say? If that was the point that I wanted to find the slope at. Well, again, it's just going to be plugging in 1 for x there. So 2 times 1 is going to be 2 again. And in fact, it really shouldn't matter if I go down to like 1, negative 3 down here, that dy dx is going to be 2 there as well. So it turns out that whatever I choose for my x coordinate, it really doesn't matter what we put in for y. And again, it's because our dy dx equation is only dependent on x. So it doesn't matter which I pair it with. At any given value of x, the slope dy dx is going to be the same vertically throughout. And that will help us to fill this slope field in pretty quickly here. So let's talk about some other values then. If x was negative 1, again, it doesn't really matter what y is, but 2 times negative 1 would be negative 2. And if x was 2, we know dy dx would be 4. But meanwhile, if x is negative 2, we know that dy dx is negative 4. And we could do the same thing for 3, 6, and negative 3, negative 6. Okay, we should probably establish what's happening at 0 as well. Dy dx, if x is equal to 0, would be 0 as well. So if we start filling in, then what does this look like here? Let's start kind of right at 0 then. We know that no matter what the y value is, when x is 0, you're going to get a slope of 0, which is a horizontal line. So you're going to draw in just little horizontal bars here on top of the y-axis. And again, this is representative of when x is 0. It could be 0, 1, 0, 2, 0, negative 27, doesn't matter. We know dy dx is 0 there. Okay, so let's move over to where x was 1. We know that the slope is 2. So we're just going to draw an approximation, but because we have this grid here, we could think of, okay, if I were to go, up 2 and over 1, approximately what that slope would look like. So I'll try and be somewhat accurate about that, but here's the first slope I'll put at 1, 0. Okay, and at 1, 1, we said, oh, the slope has to be the same there. and it has to be the same here and all throughout x equals 1, we're going to get those slopes. If I come over to -1, we just get the negated form of that slope. So I'll try and do the same slope but negative on this side. Okay. And what we're going to see to start forming here is we're going to see that as I branch out, of course, the slope is going to get larger and larger. So at 2, we now have to have a slope of 4. So that's going to be double the slope. It's going to be much steeper here. Okay, so we'll do our best there to get a slope of 4. Same thing on the other side. And again, if you think about it, even going out further, oh man, I have to have a slope of 6. And on these grids, that's going to start looking fairly vertical here, isn't it? This would be -6 out here. So I won't go out as far as -8, but we start to see a path that looks something like this. And how cool does that look? Because we know what the solution is. We know the solution, dy dx equals 2x. We know that y equals x squared plus c. So you can start to see these paths forming here of the general solution of these parabolas of the form x squared plus c. Okay, so there's an example down here that says, what is the particular solution at x equals 0 and y equals -2? Well, we know what the equation is, right? So we know in this case that it would be y equals x squared minus 2. But if I go down to 0, -2 here, again, you sort of just want to follow that as you were to sketch the parabola y equals x squared minus 2. You want to try and sketch it in a way that as you go through x equals -1, the slope is approximately, -2. And as you go through x equals 1, the slope is 2. So we're going to get a graph that looks something like, something like that. And these are just sketches, right? It doesn't have to be anything, super perfect here, but we want to try and fit a parabola in there, the parabola y equals x squared minus 2, such that we're following those slope patterns as we go to x equals 1, -1, 2, +2, or 2 and -2, and so on and so forth. So something that I think is pretty important to establish here is that because the y values did not matter, we can think of this slope field as being vertically stacked. So what that means is that on each of these vertical lines, x equals 1, x equals 2, and x equals 3, we have those same stacked slopes going vertically up and down there. So that's kind of useful in terms of when I go to make my sketch in the end, we can do that pretty easily based on the fact that if your dy dx equation is only in terms of x, this will always be true. And I'm sure you can think of what would happen if it was only in terms of y, right? So let's try another one. Let's try this one here. Dy dx equals -x over y. Okay. So in terms of thinking about what's happening here, let's start filling in the table here. Now, dy dx is dependent on x and y in this example. So we'll just have to be careful about when we sub in here, how we're going to go ahead and make sure we're marking our slopes. So for example, if I start at 1, 1, this point right here, at 1, 1, you would get 1 over 1 is 1, but then negate that, so dy dx would be -1. Okay. Let's say if I move down for a second, what about 1, 0? So at 1, 0, what's going to happen is you're going to get -1 over 0, which is, undefined. Now we know what that means though in context, don't we? We know that when the slope is undefined, that's going to represent a vertical line. In fact, shouldn't any y value of 0 produce the same thing at 2, 0, -7, 0? Those are all going to be undefined slopes, which means that we're going to have vertical lines there. So what I could do at this point is I could actually go to 1, 0, 2, 0, 3, 0. I could go as far out as I want, and along the x-axis, all your slopes will be undefined. What if I went up and down on the y-axis? If I reversed it and did 0, 1, what's going to happen there? Well, 0 over 1 is 0. So we have a slope of 0. We know that that's horizontal. So going along the y-axis here, you're going to have slopes of 0. Okay, well, let's go back to this idea of, like 1, 1 was -1, right? So that's going to look like this. Okay. What about, 2, 2? What about this point here? Well, again, if these numbers are the same, 2 divided by 2 is 1, but then we're going to negate that. So at 2, 2, we'll also have a slope of -1, and I bet the same thing will happen at 3, 3, right? So at any pair of corresponding x, y coordinates, if they're the same, you're going to get an output of -1 there. In fact, even if they're the same, but they're both negative, right? -1, -1, dividing those out, you get +1, but then we negate that. This would also have a slope of -1, so you can kind of continue that pattern over here with slopes of -1. All right, and of course we could find some other locations, but why don't we consider what's happening at 1, -1? Okay, so at 1, -1, this point here, dividing those, you get -1, but then I negate that. Now we have a slope of +1. So over here we get +1. And if I had come and done that similarly to -1, +1, the quotient here is -1, but when I negate it, it becomes +1 again. So we get this corresponding +1 slope. And according to the patterns here, you can probably take a guess that as I go to 2, -2, and 3, -3, you're going to get slopes of +1, and the same thing would happen at -2, 2, and -3, 3. Okay. And hopefully this is a good enough idea to help you start getting a sense as to what this looks like here, right? As we draw in all of our corresponding slopes, okay? So the solution to this differential equation, and maybe this derivative even looks familiar to you, but if it doesn't, hopefully you're starting to see that it looks like a series of circles, okay? So that's exactly what this is. Okay, so graphically the representation in this slope field format is a series of circles that all follow the same general pattern. And that same general pattern is that they're all centered at 0, 0. Okay. So what if I asked you, what is the particular solution? At the point 2, 0. Okay, so at the point 2, 0, we're right over here. Now, since we know that the general pattern is that these are circles centered at the origin, if this is what I've established as my radius here, I can kind of picture that we're going to contain these 4 points when I actually sketch the graph. Okay, so if I come through here, again, just make sure that at these corresponding values, these slopes are lining up here. Okay, we get a graph that looks something like that. That's not so bad. That's pretty good for me. Okay, so the particular solution specifically when at the point 2, 0 would be x squared plus y squared equals 4. And of course, we can confirm that if I were to find the derivative here, okay, with respect to x, dy dx in the end with some implicit differentiation would get you back to -x over y. So we can always double check that way that if we are getting a particular solution, its derivative should get me back here. Okay. So we're going to do one more slope field that we draw together. And this last example is going back to the one from the start of today's notes. So at the start, we were like, hey, if I said find y given dy dx equals 1 over 1 plus x squared, we didn't quite know how to do that. So even though we still don't know how to do it algebraically, I hope that after looking at this example, we can start getting a general sense as to what y would look like in this slope field. And then once we kind of get a sense of what it looks like, maybe I'll have you make some guesses as to what you think y equals. Okay, so let's start with x equals 0. So at x equals 0, does it matter what the y value is for 0, 1, 0, 2, 0, 3, 0, -1? Because this is dependent solely on x, this column will not matter. Doesn't matter. Okay. It doesn't matter what you choose for y. At any x value of 0, the y coordinate doesn't matter because dy dx is always 1 over 1 plus 0, which is 1. Okay, so let's go ahead and start sketching that then. So if we have a slope of 1 here, we'll just copy that same slope here, here, here. Okay, so let's branch out from there. Then what if I plug in x equals 1? So if I plug in 1, we get 1 over 1 plus 1 squared, which is 1, so that's 1/2. And let's also test -1 while we're at it. And what we should realize is that this is going to have some symmetry here, because when I plug in -1 squared is also 1. So we get 1/2 there as well. Okay, so a slope of 1/2, if we think about from each of these x values of 1, going up 1/2 and connecting the slope there, that might look something like this. Okay, so drawing those slopes of 1/2, same thing at -1. Okay. So let's go one step further. Let's do 2 and -2. If I plug in 2, 2 squared is 4 down there. So 1/1 plus 4 is 1/5. So now our slope is getting definitely significantly reduced there. So 1/5 is going to start looking something like this. Much less steep. And maybe we'll just go out one more after this. Okay, these are all going to be positive slopes according to 1/1 plus x squared. And finally, the last case is 3 and -3. So if I plug in 3 squared is 9, -3 squared, also 9. So we get 1/10 as the slope there. And these are going to start looking fairly horizontal at this point, right? They have a very tiny slope of 1/10. So it's going to start looking pretty horizontal. Not quite horizontal, but that's the general shape. Okay, so these are pretty cool looking graphs. I mean, they kind of look like magnetic field lines to me, if you guys are familiar with looking at paths of magnetic fields at all. I don't know if you do anything like that in physics, but that's what it starts to look like when you draw on all of these slopes. So what's the general path here for what y would equal, right? We're sort of unsure. So y equals, not sure. But if you were to draw that general path in, it's definitely going to be a curve that the slope of the curve starts to increase as I approach 0. It has the biggest slope at x equals 0. And then as you go through 0, then the slopes start to decrease, right, for dy dx. So think about what type of function could model this. And when I see you next, I'm going to ask you, what do you think? Because you should be familiar with graphs that kind of look like this general pattern. So there's some good options as to what you think could be the case. But in the end, I want you to see if you can think of it. And by the way, if you think of an example of what you think this is modeling here, see if you can find the derivative and see if it matches 1/1 plus x squared. All right, so we'll do that next time I see you. All right, last thing I want you to also try on your own, and I'll give you a little bit of time to talk about this with some friends in class. Match the differential equations below with the graphs of their slope fields. So given each of these dy dx equations up at the top, they each correspond with the slope field down here. So think about some good tricks that would help you to be able to match some of these up, right? We actually did this one already today, and remember that when we're talking about things that are only in terms of x, those should be vertically stacked. So in fact, the last example, we should probably make a note that this was completely vertically stacked. Whereas if it was all in terms of y only, oops, sorry, you couldn't see that. But if dy dx is in terms of y solely, then we're going to see something that's horizontally stacked. In terms of x and y, we did one like that today, where we had our circle. It's not that it will always look like a circle. But when in doubt, maybe make a quick list, choose some x and y values, right? Make that table for x, y, and dy dx. That should be able to help you establish and match which one of these slope fields matches with these differential equations, okay? So we'll go over that next time we're in class together and eventually be able to do slope fields on our calculator using the program that everyone should now have. So that's it for day 38. Have a great rest of your day.